Okay, analysis 1A. Hello. We are going to go over the rest of this packet called Final Assignment on Limits, which is really hard. This packet is a slight modification of what I would normally pass out and call it, review packet or something like that. And then you would do this whole packet and you'd be like, man, this all stuff is so hard. But then you'd learn, and then there would be a big test on limits that would be, easier than this packet. So that would be great. Anyway, Zoom School. Instead, I just dropped this packet on you, and you may have found it to be very hard. These two problems are not so hard. Let's go. The limit as x approaches infinity of the square root of 9x squared plus x minus 3x. Well, I don't have a lot to say because we've done already a lot of problems like this. So, what's the situation? The situation is that as x goes to infinity, this goes to 0. As x goes to infinity, this term goes to infinity, but this term also goes to infinity. So this is an infinity minus infinity situation. And hopefully you're now aware that this is indeterminate, and so we cannot guess what the answer is to this problem. You might at first think it's 0, but it might be 0, but it might not be. How can we do this problem? Well, I need to see precisely what the gap is between these two things, and so I need to multiply by the conjugate. So that's what I'm going to do. I multiply by root 9x squared plus x plus 3x over root 9x squared plus x plus 3x. And yeah, that's it. So what do we get? Let's see if I can squeeze this over here. This becomes the limit as x approaches infinity of the top now kind of clarifies itself. It becomes, via the difference of squares, 9x squared plus x minus 9x squared. And now I've sort of created a mess on the bottom, but maybe that was all worth it. And I think it was because the 9x squareds cancel, and we get the limit as x approaches infinity of, just x over root 9x squared plus x plus 3x. And now I think you can already just guess what the answer is to this problem. Therefore, this problem is really not that hard. It's hard the first time, but if you repeat something over and over again enough times, it kind of becomes easy. What's happening as x goes to infinity? Well, both the numerator and denominator are getting very, very big. So we need to compare them. How? By pretending that this is kind of like a rational function. And if I divide the top and bottom by the highest power in the denominator, which is effectively just x, because a quadratic that's being square rooted is more or less like a linear function, end behavior-wise. And so now this is the careful way to do this problem, I distribute the 1 over x through, which makes just like 1 on the top, but on the bottom, let's do this just kind of all in one step. 1 over x is really like root 1 over x squared, so when you put 1 over x back in square root jail, it becomes 9 plus 1 over x. Alright, because we've done so many problems like this, I think it's okay for me to skip those steps. And yeah, why is that good? Because now everything has been clarified. As x goes to infinity, 1 over x goes to 0, of course. So this is 1 plus root 9. Sorry, this is 1 over root 9 plus 3. And so the answer to this problem is just 1/6. Okay, cool. Cool. Next is a proof. This is the kind of proof that, we actually never did one of these in class. Perhaps we did. Can't remember. I believe not, though. Anyway, this is one of those proofs. The proof is not hard. The hard part is even just figuring out what it is that you're supposed to be doing. What are we supposed to be doing? Well, we have this function, natural log, and we want to show that the limit as x goes to 0 plus is negative infinity. Let's make a picture. It looks kind of like this. Here's 1 and something like that. So indeed, it is just a kind of accepted fact of pre-calculus that that for very, very tiny positive values, the natural log is a huge negative number. Okay, so I want to make statements like this, and so I better have a precise definition of what I mean when I say that this goes to negative infinity, because negative infinity is not a number, and we have a precise definition of what we mean when we say negative infinity. This is kind of shorthand, so to speak, for the following idea. Let's talk it out. Near zero, the natural log becomes a huge, huge negative. And then you might sort of say, well, how huge of a negative? And the answer is, as huge of a negative as you might want. And so given any challenge whatsoever, and what is that challenge? That challenge is, if you're saying this is going to negative infinity, then you're going to get challenged with a number like negative a million, right? That challenge comes in the form of a massively large negative number. I use m for massively large negative number. And what do I do to meet that challenge? Well, it's near zero that the natural log function is supposed to become negative huge. Therefore, the way I meet this challenge is by getting close enough to zero so that the function is less than the massively large negative challenge that you made. Okay, in other words, I need to find a delta. And here, we're taking the limit as x approaches 0, so delta is the distance from 0, and only on the right-hand side because we're only taking the limit as x approaches 0 plus. All right, therefore, half the challenge here to you in doing this proof is realizing what it is that we need to prove. And these definitions were all in the book, but maybe this is the first one ever of these that you're actually doing. So that's fun. What do we need to prove? We need to prove that for any massively large negative number m, there exists a response. And the response is some positive number delta. And what is true about that positive number delta? Well, it represents how far away I'm allowed to drift from 0 on the right. And while the outputs of the function are still less than the challenge. Or maybe it's a better way to put it is, delta represents how close to 0 I must get in order that the outputs of natural log are less than the challenge number. And so that's basically it, right? If x is a number between 0 and delta, that's really the claim I'm making, right? That delta is how close I need to get. So all the numbers less than delta, all the positive numbers less than delta, all have the following property. That f of x is less than m. Okay, so this is more or less like a kind of a generic explanation for what it means for the limit as x approaches 0 plus to be negative infinity. Okay, and I think it just all makes sense if you just draw the picture and think it out and kind of talk it out to yourself. Okay, well, understanding what I need to prove, I get a challenge, I respond with a delta. As long as I stay within delta of 0, the outputs of my function are less than m. And of course, okay, and now that I understand that, well, whoa. I just jumped. Got scared there. Alright, so now I just need to prove this. Making a video. Whoa. Not sure whether it's a very professional operation here. Not sure whether I was on camera or not when I jumped up in the air. But didn't see that person coming. Woo! Yeah, the bigger the massively large negative number that you challenge me with, then the smaller delta has to be. Intuitively, if m is like negative 1,000, then delta is going to be very, very small. But if m is like negative 1,000,000, then delta is going to be even smaller. Thus, the delta I pick depends on the m challenge I receive. And that's why I need to go into a discovery phase to find the appropriate delta response to that m challenge. What do I need to be true? I need it to be true that my function is less than m. And what is my function? It's natural log. So I need natural log of x to be less than m. And okay, well, when is natural log of x less than m? I'm just going to e up both sides of this. So this will be true when x is less than e to the m. And okay, yeah, both natural log and the exponential function are sort of increasing and one-to-one. So, you know, that's what the exponential function looks like. And so it's certainly true that if you have two numbers, then the bigger number is going to have the bigger, you know, e to the b is bigger than e to the a if and only if b is bigger than a. In other words, it's correct even for negative numbers. It's correct for us to go from here to here in the proof and vice versa. So, does this actually make any sense? Yeah, I think it does, because remember, what kind of number is m going to be? M is going to be a number like negative 1,000. And so, if you give me a challenge like negative 1,000, e to the negative 1,000 is, don't forget, that e to the negative 1,000 is really like 1 over e to the 1,000, which is e to the 1,000 is an incredibly huge number. And so 1 over e to the 1,000 is an incredibly small number. And in fact, yeah, so that's what I'm saying, right? Let x be less than that number and everything's going to be good. Okay, so my conclusion is I should just set delta to be e to the m. Okay, if you get that, cool. If not, maybe you'll appreciate it now when we go to do the actual proof, because here comes the actual proof, which is very short. There's not that much to write. It's more about understanding. Well, how does the actual proof go? I first receive a challenge. The challenge comes in the form of this huge negative number. So take m less than 0. What is m? It's a giant number like negative 1,000,000. My immediate response is to set my delta to be e to the m. And like I said, if m is a big number like negative 1,000 or something, then e to the negative 1,000 is a tiny, tiny, tiny positive number. So maybe just like, I don't know, I want to say like note, you know, delta is positive or something like that, because e to the anything is positive. And my claim is that, you know, that's the right delta. What do I need to do? Well, I need to show that my delta works. And so I need to show that if you give me any x value between 0 and delta, that when I take the natural log of it, it's less than m. Okay, so how do I establish this conditional? Just by doing the proof. So assume that x is some tiny number which is positive but less than delta. Well, I defined delta to be e to the m, and so I know that x is a tiny positive number that's less than e to the m. And okay, so keeping in mind that x is positive, I know that x is less than e to the m. Well, if x is less than e to the m, then ln x, just take the natural log of both sides, ln x is less than m, and actually that's just the whole proof, right? That's what needed to be shown. And so really, actually, the proof is basically just one line, really. It's x is less than e to the m, so ln x is less than m. And that's justified because, as I mentioned in a previous video, I think the natural log function is also one-to-one and increasing. And so if you give me two numbers that are in a certain, where one is less than the other, so is the natural log of them in that same relationship. Okay, that's it. Good. Back in a second with more. Okay, we are back. Page 6, number 14. This whole page is just one big problem. The problem is, analyze this function, square root of 2x squared plus 1 over 3x minus 5. What is this function? It's just a just a function. And you could argue that this is really just pre-calculus, and I would agree. Because this is the kind of thing that we do in pre-calculus. We take functions and we look at all their properties, you know, end behavior, asymptotes, roots, you know, x, y intercepts, etc., and we try to make a reasonable sketch of that function. However, many of the facts I wish I had about functions when I was in pre-calculus, I don't actually learn those facts or how to get those facts until we get to calculus. So a big part of this course will be kind of using every new little calculus skill that we learn. We can now look back on pre-calculus and figure some things out. Okay, well here is a function which is kind of like a rational function, and so this is the kind of problem you could potentially do while you were studying rational functions. But it's not actually a rational function because the numerator is a square root function, not a polynomial. Well, we can still basically use all the techniques of pre-calculus, and now I will add in my new skill, which is just being very good and very confident about limits. So this is also a problem, kind of an excuse for why we learn limits, or sort of this is a practical application of limits. It's not practical at all, but we can use limits to help us analyze, you know, some complex function like this. Okay, let's go. Maybe even before we do these limits, we should just like do some simple pre-calculus observations. What's one observation? Well, the numerator, the square root of anything, is going to be positive. So this numerator is always positive. The denominator will change sign at 5/3. So actually, I can't plug in 5/3. So that's maybe we should do all these things, right? What's the domain of this function? Well. If I square anything, it's positive. Multiply it by 2, it's still positive. Add 1 to it, it's still positive. So the inside of the radical in the numerator is always positive. Therefore, there are no inputs which will disturb the numerator. So I think the only problematic input is 5/3. Therefore, I claim that the domain of this function is everything except 5/3. All right, that was kind of nice. While we're on the topic, does this function have any roots? I say no, because, like I just said, that numerator will never be 0 because 2x squared plus 1 will never be 0 because it's always positive. In fact, it's always greater than or equal to 1. So, alright, I got my domain, I got that there are no roots. Maybe I want to just plug in 0. That's always a nice thing to do. What is the f of 0? It kind of gives you like a free point. Well, you get the square root of 1, and on the bottom you get, so I guess I get 1 over negative 5, so that's negative 1/5. And then the thing I really wanted to do is to analyze the sign of this thing, and the sign of this entire function is going to be determined by the sign of the denominator, and the denominator changes sign at 5/3. It's just a line, which is negative and then positive. Alright, so I got a sign chart, I found my roots, I found my y-intercept, I know the domain, so all that's just kind of like good stuff that we should always do. Okay, now let's bring in the calculus, which is really barely calculus. What's the end behavior of this function? Well, you can basically just eyeball it, right, by plugging in like 1,000. If you plug in like 1,000, it's 3,000 on the bottom, and it's the square root of 2 times 1,000 squared is a million. The square root of 2 million is going to be like root 2 times 1,000, so I think this is root 2 over 3. That's exactly right. How can I show this more carefully? I'm not going to give a long explanation again because we've done now like a lot of these problems, I think. The strategy is going to be to divide by the highest power of x in the denominator, and for this one also. Okay, well, if we do that, what do we get here? Well, let's see, how much work should I show? I guess all of it. 1 over x is really like root 1 over x squared, and that's a fact. And this becomes, when I distribute the 1 over x, just 3 minus 5 over x. And over here, something very similar is going to happen. But now there is this kind of subtlety, which is that as x goes to negative infinity, I'm plugging in a large number like negative 1,000 in here. Well, that's going to be like negative 3,000 on the bottom, but the numerator is going to be positive. So I'm not going to get the same thing. in fact, when I choose this algebra step here, and I distribute the 1 over x through, yeah, I get 3 minus 5 over x, but as I've explained a couple other times, 1 over x, when x is negative, is not root 1 over x squared. It's in fact negative root 1 over x squared. So this is perhaps a little bit of a tedious explanation that maybe it's better to just use common sense and to recognize that here you're going to have positive over negative and here you're going to have positive over positive, so these can't be the same. But one way or another, my explanation is that in the first case, 1 over x is equal to root 1 over x squared. In other words, those two green things are equal when x is positive, but it is a fact of arithmetic that when x is negative, those two red things are in fact equal. So that's kind of a bookkeeping device for getting this problem right. Anyway, when I then multiply through these radicals, I get root 2 plus 1 over x squared, and this is 3 minus 5x on the bottom. But for the other one, kind of doing these two simultaneously to compare them, now that negative is on the outside, so when I combine these square roots, I get negative root 2 plus 1 over x squared over 3 minus 5 over x. And so, like I have been saying, this goes to 0, this goes to 0, this goes to 0, and that goes to 0. And so, this first limit is going to end up as root 2 over 3. But the second limit is going to be negative root 2 over 3. Okay, so potentially the sort of technical skill in evaluating limits has helped us realize that this function has two different horizontal asymptotes. And I think somewhere on the paper it says something like, justify, that the function has a horizontal and vertical asymptote. So let's do that now. Maybe I'll note something, which is that root 2 is about 1.4. So this is not so different from this is about this is about 1/2. Let's just call this roughly a half, because it is roughly half, and that's roughly negative a half. And now, in a new color, like purple or something, I will squeeze in that the very definition of horizontal asymptotes is that the end behavior is that number. So after concluding that this is 1/2, I could say something like, so f has a horizontal asymptote at y equals root 2 over 3. So the justification of the fact that the function has the horizontal asymptote is simply the demonstration that the limit is 1/2 as x goes to infinity. And the demonstration, and also, alright, so f has a vertical asymptote at y equals negative root 2 over 3. Okay, good. Over here now, this is I think a little bit easier. Of course, near 5/3, this denominator is going to be very, very tiny. So tiny that 1 over it is going to be huge. And so this is going off to sort of infinity in both directions. So this really is just pre-calc. In fact, I even made a sign chart, which is reminding me that the numerator is always positive. So I can just look at my sign chart and see exactly what the answer is. There's really almost no work to be shown here. But if you want to show some work, you can just say something like, alright, if I plug 5/3 into the top here, I don't really care what this numerator is. All that matters is that it's some kind of positive number. And in the denominator here, if you give me a number a little bit less than 5/3, then 3 times a little bit less than 5/3 is a little bit less than 5. And a little bit less than 5 minus 5 is going to be a tiny negative number, and so this is negative infinity. I think the easier thing to do is just to look at the sign chart and see that it's clearly infinite near 5/3, and the sign chart tells you that it's negative infinite. That's the kind of thing we did in pre-calc. Anyway, if x is a little bit more than 5/3, and it's still true that this numerator will be a positive number, but the denominator now, if you multiply 3 times a number a little bit more than 5/3, it's a little bit more than 5. A little bit more than 5 minus 5 is going to be a tiny positive number, and so this is going to infinity. Okay, And getting out the purple, since this is negative infinity, I can now conclude, so F has a, oops, that should say horizontal asymptote. Here I now want to say that F has a vertical asymptote at x equals 5/3. Okay, what's the definition of what it means for a function to have a vertical asymptote? Well, at a certain point, like 5/3, well, it just means that at that point, from either the left or the right, the function goes to either infinity or negative infinity. So, okay, good. Done with that. I did my 4 limits. This is all building towards being able to graph this function, I guess. Graphing is kind of an excuse to be doing these limits. Well, what do I know? First off, I know that there is a vertical asymptote at 5/3. What happens when I plug in 0 again? I get some tiny number like negative 1/5, so I might as well throw that in. And what else? Well, there's some kind of asymptote of 1/2, so I have like a this type thing, cha-cha-cha-cha-cha-cha. And also, maybe it's actually more clear to only draw that horizontal asymptote over here on the positive side, because only off to positive infinity do I get that kind of end behavior. And then for negative infinity, I get a different horizontal asymptote. So now, what does this function look like? Well, there's about one more thing I want to know, and that is, does this function ever cross its horizontal asymptote? Either one. So what I'm going to sort of pose, the question I'm going to sort of pose right now is, does f ever equal root 2 over 3 or negative root 2 over 3? So are there any x values which, when I plug them into this function, give me back either root 2 over 3 or negative root 2 over 3? And I think the answer turns out to be yes. How can I solve this? Well, I am going to just do it, right? This is the function. Does this function ever equal plus or minus root 2 over 3? Now, you might think that you need to solve these two things separately, but almost the first thing I'm going to do is to, got really dark all of a sudden, is square both sides anyway. And so actually, I can solve sort of both of these equations kind of in one step, because they turn into the same equation. So just before squaring both sides, I'll cross multiply just because I feel like that's easier. So I get 2x squared plus 1 equals plus or minus root 2, 3x minus 5. And then now I just have a little algebra problem. How do I solve this algebra problem? Well, I'll just square both sides. And I get 9 times 2x squared plus 1 equals 2. And then this is 9x squared minus 30x plus 25. Alright, so that's 18x squared plus 9 on the left, 18x squared minus 60x plus 50 on the right. Hopefully I don't make a mistake. Yeah, well, what do I end up with? I end up with 60x, the 18x squareds cancel. I get 60x equals 41, and so x is 41 over 60. Okay, so it appears that when x is 41 over 60, that I will, in fact, cross one of these asymptotes. Which one? Well, I just kind of already know that any number less than 5, for any number x value less than 5/3, the function is negative. And so now going to 41 over 60, going to 41 over 60, which is like 2/3, I see that my function must be negative there, and so it must be the asymptote y equals negative root 2 over 3. So I'm going to put a little dot right there, and finally, am I kind of like done? Oh, so it crosses there and nowhere else, right? That's what I gained from this algebra. I gained the knowledge that only for x equals 41 over 60 and no other x values does this function equal either this number or this number. And so I'm ready to graph this thing now, basically. What do I know? At negative infinity, I am very close to negative root 2 over 3, and it must be the case that I'm just above that asymptote because I only cross it one time, which is here. And so I got some kind of thing like this. Now I cross. By the way, I kind of know that I really do cross here. This is not some sort of phantom solution, because after all, what happens to the left of 5/3? I end up down at negative infinity. So to the extent that this function is continuous, and it is, because it's just the ratio of two continuous functions, except at 5/3, of course, I know that since my function is at negative 1/5 at time 0, and then at a little bit less than 5/3 goes down to negative infinity, I sort of have to cross somewhere. And what I've learned is that cross point, where I cross that lower horizontal asymptote, is in fact 41 over 60 comma negative root 2 over 3. Oh yeah. And now what happens if x is a little bit more than 5/3? I'm up at positive infinity, and I know I never cross this asymptote, this y equals root 2 over 3 horizontal asymptote. And the end behavior is just root 2 over 3. Alright, so I'm not claiming that this graph is perfect. In particular, I'm not sure. There's going to be some sort of relative maximum. I don't know where that is. But this is certainly as good as anything that we graphed back in pre-calc. It's kind of a sketch, I guess, if you adopt that term for a graph that's not totally accurate. But it is accurate with respect to behavior near x equals 5/3, end behavior, roots, crossing the asymptote, and everything else. Okay, woo, that was a pretty hard problem. Back in a second with an even way harder problem. Okay, hello, number 18. This problem is so hard. Where did this problem come from? This is like kind of like, you know, if you mastered the previous problem and you're looking for more of a challenge, here's an even harder problem. And okay, this is, in some ways, this is kind of just pre-calculus still, sort of. But again, using the math that we practiced over the course of this unit, we can calculate these limits, and then that will sort of tell us what we need to know about this function. Where did this problem come from? I used to tutor a kid taking pre-calculus at a prominent, rich private school in which they had a very, very fancy, very, very hard pre-calculus class that was as hard as the magnet program, seemingly, but it was private school, so I don't know, it was kind of weird. The problems were really hard, but everyone would just like fail all the tests, but then they would just get B's anyway because private school. So there was a test that was like 2 questions or something, and it was graphing rational functions, and this was one of the problems on the test. And of course this kid is not going to get this problem. No one is going to get a problem like this in a test situation on the spot. And I think they were given no tips or hints or clues or anything. They were just said, you know, make an accurate graph of this function, you know, go. So alright, I thought that was really hard, and while going over this problem for like an hour with this kid, teaching him how to do it so he could submit his test corrections and get an A anyway, even though he had failed the problem, I thought, this is a good problem for my students, and I will type it up and assign it on some kind of review packet. And but I will be nice and like kind of break the problem down into little pieces for my students so they can have some hope of getting this done themselves. All right, so you know, if you find this page to be like way too hard, just write something on the page like, sorry Mr. Rose, too hard, you know, Zoom school, I'm not doing this page. That's probably fine. But for the rest of you who want a challenge, let's go. The world's knowledge is available to us. We just have to look carefully. I got a function here. What can I say about this function? Well, first off, definitely can't plug in 3. So that's worth noting. X can't be 3. Anything else that x can't be? Well, yeah, x, I have to worry about this square root function now. And in fact, maybe we should just see what the roots are, since that was another kind of prompt. When does this function have roots? Well, it will have roots when the numerator is 0. So let's see, when the numerator is 0, you could kind of just do this in your head, but alright, when is root x squared minus 5 minus 2 going to be 0? Well, of course, that's just when root x squared minus 5 is 2. When is that? Well, when x squared minus 5 is 4, squaring both sides. When is that true? When x squared is 9, and so that's when x is going to be plus or minus 3. So if x is either 3 or negative 3, seemingly, then I'm going to have a root. But alright, I already agreed that this function doesn't exist at x equals 3, so I don't even know what to say now. I can't plug in 3. Maybe I can plug in negative 3 though. What happens if I plug in negative 3? Well, if I plug in negative 3, I get 9 minus 5 is 4 minus square root, which is 2, so I get 0. And when I plug negative 3 on the bottom, I get negative 6 minus 6, that's negative 12. And so indeed, f of negative 3 is 0. So this function has some kind of mysterious behavior going on at around 3, which I've yet to investigate, but I do have one and only one root, and that's at negative 3. Okay, so that was good knowledge. But alright, while doing this, I kind of have a better sense of this function now. And one thing I notice is that this thing underneath the radical could be negative. If x is 1, for example, then 1 squared minus 5 is negative 4. I can't take the square root of negative 4, so this function will be undefined. So when will this function be undefined? Maybe it's simpler to say when it is defined. When it is defined is when the x squared minus 5 is greater than or equal to 0. I sort of need the inside of that radical to be greater than or equal to 0. Alright, that means I need x squared to be greater than or equal to 5. Therefore, if x squared has to be greater than or equal to 5, then that means I need x to be greater than or equal to root 5, or x to be less than or equal to negative root 5. And so it's under those conditions that my function will be defined. Therefore, what's my domain? My domain is going to be, let's just write it out, it's going to be everything from negative infinity to negative root 5 is okay, inclusive, because if I plug in negative root 5 I get 0 underneath the radical, so everything's okay. But then, gotta write maybe a little bit smaller now, anything between negative root 5 and root 5 is going to be undefined, so I pick it back up again at root 5, but then root 5 is about 2-ish, then it's undefined again at 3, right, as we already discussed. So this is going to be up to 3 union everything from 3 to infinity. So that is my statement of the domain. It's basically x has to be bigger than root 5 or less than negative root 5 and also undefined at 3. Yikes, that was pretty hard. Alright, another thing I want to do is a pre-calculus thing, which is to make a sign chart for this function. Man, that is really hard. Because, well, okay, well, I don't know, maybe it's not that hard. Let's do it. How are we going to do this? I think the maybe most organized approach is to make a sign chart for the numerator and a sign chart for the denominator separately and then sort of multiply them. Okay, so let's do that. What is the sign chart for the numerator? Well, basically, let's just talk it out. Basically, when is the numerator going to be positive? The numerator is going to be positive when root x squared minus 5 is bigger than 2. When will root x squared minus 5 be bigger than 2? Well, when x squared minus 5 is bigger than 4. When is x squared minus 5 bigger than 4? Will be when x squared is bigger than 9. And x squared will be bigger than 9 to sort of to the left and right of negative 3 and 3. Alright, so I don't feel like writing all that out all over again because it's kind of a repeat of what we already talked about. But if you followed all of that, and I think you can follow it, I get something like this as my sign chart for the numerator. If x is bigger than 3, like, I don't know, 4 say, then, then we're good. And we're going to get, 16 minus 5 root 7. So, okay, I think what's tricky is that there's also this kind of domain problem. But I'm sort of ignoring that for the moment because there are numbers that are, well, let's just keep going. What about the denominator? The denominator, that one's easier. That's going to change sign at 3, and it's going to go from negative to positive because it's just a line. So there's 3, and this is going from negative to positive. Therefore, when I multiply them together, I get the following sign chart. Well, here's negative 3, and here's 3. To the left of negative 3, the numerator is positive, and the denominator is negative, so the product is negative. In between negative 3 and 3, the numerator and denominator are negative, so the product is positive. And when x is bigger than 3, they're both positive, so the product is positive. Okay, that's not terribly wrong, but it's kind of wrong because, of course, the domain of this function means that this function actually just doesn't exist in between negative root 5 and root 5. Okay, so the real answer, this was kind of like, not quite or something, but this is like the real answer to the sign chart for f goes like this. Everything I just said above was correct, except for, so it is true that it's negative to the left of negative 3, but then like at, and maybe now I'm going to introduce like a dot or something, dot, in between negative root 5 and root 5, the function just doesn't exist. But then there's still a little bit more space in between negative 3 and 3. So okay, so it's going to be positive from between negative 3 and 3, but also for a big chunk of that space in between negative 3 and 3, it just doesn't exist. So that's what I've kind of indicated here with those dots. And then beyond 3, it's just positive. Okay, so that took a lot of effort, and I haven't even done anything yet. I have just made the correct sign chart for this function. Whew! Okay, now let's do these limits. Well, I'm just getting really good at this now because this is just kind of a repeat of what we already talked about in the previous problem. So I will divide the top and bottom by x because this is kind of like a rational function even though it isn't. And just like before, I'll do these two kind of simultaneously because the algebra is almost exactly the same. The difference is in the sign of x. And so this becomes the limit as x goes to infinity. Alright, well if you made it this far and you're still watching, then maybe I don't need to go through this whole explanation again. That is, since x is positive, when I put 1 over x back in jail, it becomes 1 over x squared, and therefore this becomes the square root of, putting it back in jail, 1 minus 5 over x squared minus 2 over x over 2 minus 6 over x. And whereas, since x is going to negative infinity now, then when I put the 1 over x back in jail, it leaves a kind of negative behind, and this becomes 1 minus 5 over x squared minus 2 over x over 2 minus 6 over x. Okay, so it's like Jean, and of course, as x goes to infinity, all the things that go to 0 go to 0. Maybe I won't even write it because it kind of clutters things up a little bit. And we get just 1/2, is that right? Yeah. So here we have 1/2, and here, as x goes to negative infinity, we get -1/2. It's also possible to just sort of feel this by, like I was doing before, plug in 1,000. If you square 1,000, you get pretty much 1,000,000. Taking 5 off of that is not going to change much of anything. So the square root of that is still pretty much 1,000. The 2 is irrelevant. The 6 is irrelevant. So this is basically 1,000 over 2,000, so it's just got to be 1/2. Whereas over here, if you plug in -1,000, then when you square it, you get 1,000,000, positive 1,000,000. 5 isn't going to change much. The square root of that is basically 1,000 minus 2 is still basically 1,000. So I get basically 1,000 on the top, but I get basically -2,000 on the bottom. And so that's 1,000 over -2,000, which gives me a answer of -1/2. Okay, what do I conclude? I conclude that I have a horizontal asymptote of y equals 1/2 on the so-called right end behavior, and a horizontal asymptote of y equals -1/2 on the left end behavior. Alright, so if you made it that far, we got the end behavior now. Maybe I'll even add that to my graph, so I just feel like I'm making some progress. So here's my 1/2, and here's my -1/2. And hey, let's not forget that this function is just undefined between -√5 and √5. So what is √5? It's like 2 point something. So maybe I should just add that in right now to my picture. That here is √5, and yeah, it's a little bit more than 2. This is going to be -√5. That's going to be a little bit less than -2. And this function just simply doesn't exist in between these two. Maybe I'll even erase my x-axis or something crazy like that. Just so you kind of remember. That looks really dumb now, but too late. Just so you remember that this function just does not exist in between -√5 and √5. Okay. Yeah, I guess that looks okay. Whew, what next? Well, something weird is happening near 3. What is happening near 3? Man, I wish I knew. Well, when I plug 3 into the function, of course, I get 9 minus 5 is 4, square root of 4 is 2, so I get 0 over 0. Aha, a 0 over 0 situation. And so it's unclear what's happening. In fact, a casual pre-calculus student might think that there was some vertical asymptote at x equals 3. Because after all, if you just look at the bottom, you see that when you plug in 3, that the bottom is basically 0, so you might think that the function becomes like infinite or something. And maybe you're right. Let's find out. Well, it's a 0 over 0 situation, so that just means we have to do this limit. Okay, but ho-hum, we're just really good at doing this kind of limit. How do we do a limit like this? Answer, when it's indeterminate 0 over 0, we need to multiply by the conjugate. And so we're just going to do that now. Going to multiply by root x squared minus 5 plus 2 over root x squared minus 5 plus 2. And now, what do we get? I don't know. Let's keep on going. This becomes the limit. As x approaches 3 of, well, I get on the top then x squared minus 5 minus 4 over 2x minus 6 times root x squared minus 5 plus 2. Alright, well, I think you see where this is going. That's x squared minus 9 on the top, so I can cancel that. So I get limit. As x approaches 3, on the top I get x minus 3, x plus 3, and on the bottom I get 2x minus 3 times root x squared minus 5 plus 2. And the x minus 3's cancel, and the thing is just now no longer indeterminate. And so maybe just writing it out one more time, this is therefore the limit as x approaches 3 of x plus 3 over 2 root x squared minus 5 plus 2. And what is that? Well, now if I just plug in 3, I get on the top 6, and on the bottom 9 minus 5, 4, square root of that is 2, so that's 4 times 2 is 8. And so the answer to this is 3/4. Yikes. Okay, so if you do all of that stuff right, here's what I just have learned. I've just learned that, well, the limit as x approaches 3 of this function is 3/4. But of course also this function is sort of undefined at 3. We know. That means there must be some kind of hole here at 3, 3/4. So I'm just going to put a hole there. And maybe I'll label it like later or something. Alright. Oh my gosh. So does this function have any vertical asymptotes? It doesn't. Does it have any roots? It does. Let's see, I guess I'm gonna graph this thing in purple. So I'll put a root at -3. Does it have a y-intercept? That's something worth doing. Oh, of course, no it doesn't, because 0 is outside my domain. And so it sort of seems like I'm not going to get much more out of this function, except maybe I want to plug in root 5. Alright, so this part is now getting a little bit silly, but if you plug in root 5, what happens? Just doing this whole problem as if calculators weren't invented, if I plug root 5 in here, what do I get? Yeah, I'm going to get -2 over 2 root 5 minus 6. So whatever that is this what I actually did on my paper? Yeah. So that is, let's see, if I divide the top and bottom by -2, that gives me 1 over 3 minus root 5. And of course you could leave it there, but here comes the crazy world of mean old-fashioned teachers who try to force you to do obscure things like don't ever leave a irrational number in the denominator. Why do they do such crazy and obscure things like that? Because, you know, once upon a time, when you could only do things by hand, then this is a good way of simplifying this, and by simplifying I mean making some sense out of this. What do I get down here? 9 minus 5, which is 4. And so the answer to this is 3 plus root 5 over 4. And it's certainly much easier to estimate this function when it looks like that. What is 3 plus root 5 over 4? Man, I don't know. It's like 5/4, pretty much. So I'll just write, 5/4. Okay, I'm writing kind of small because I'm getting in the way of my graph. So let me then just do the same thing for f of negative root 5. Now what? I still get -2 on the top, but now on the bottom I'm going to get 2 root 5 minus 6. So all the negatives cancel. I get 1 over 3 plus root 5. And I will now, I really don't have to do anything to be totally honest. This is just pretty clear already, just as is, that 1 over 3 root 5 is just pretty much like 1/5, I guess, or something like that. So this is basically 1/5, and this is basically what I say, 5/4. Okay, so after all that, I'm ready to graph this function for real. Where am I at negative, oh no, I'm even not ready. Oh my god. Where am I at x equals root 5? I'm up here at 5/4. So, I said I was doing this in purple, right? So I'm up here at 5/4. Cha. What is that point? It's root 5, 5/4. Good. And, yeah. Then, where am I at negative root 5? I'm at positive 1/5. So boom, that is negative root 5 comma, well, it's not really 5/4, right? It's actually, yeah, this is actually like 3 plus root 5 over 4, and this is actually 1 over 3 plus root 5, or you can rationalize that if you want to. Okay, man, about one more thing left to do. Does this function ever cross its horizontal asymptotes? I don't know. So I better find out. Let me clear a little bit of space here and let me get to work. Does my function, which is root x squared minus 5 minus 2 over 2x minus 6, does this ever equal 1/2 or negative 1/2? Okay, so now I just have some algebra to solve. So let's do it. I can multiply both sides by 2, and that gives me root x squared minus 5 minus 2 equals, actually maybe it's just easier to say multiply both sides by 2x minus 6. If I multiply both sides by 2x minus 6, the 2 cancels the 1/2, and so I'm just going to get plus or minus x minus 3, if you followed that. Geez, now what am I supposed to do? I guess the only thing to do now is to just, yeah, I'm going to square both sides as is. Is that really what I'm going to do? Yeah, wow. Okay, so square both sides as is. If I do that, I get x squared minus 5, so that squared, minus 4 root x squared minus 5, because I don't want to lose any solutions, because this really is plus or minus. So then I get plus 4, so that's the square of the left-hand side, equals, and then when I square this side, the plus or minus disappears, and I get x squared minus 6x plus 9. So, what now? Oh my gosh. So the x squareds cancel. This is like hard. The x squareds cancel, and I am left with, let's just do it carefully. I'm left with negative 4 root x squared minus 5 minus 1 equals negative 6x plus 9. Okay, so now by doing a lot of move, let's see, that becomes 10, but then I'm going to swing it over to the other side anyway. So this becomes 10, oh my god. Wait, what? 6x minus 10, I guess, equals 4 root x squared minus 5. Hold on, I'm losing confidence in my Algebra 1 skills because I'm running out of board space, so I'm getting sad, but yeah, that's just right. 6x minus 10 equals boom boom. Okay, I can divide through by 2, so this is really like 3x minus 5 equals 2 root x squared minus 5. And now there's nothing to do except keep on going. Square both sides again. I get 9x squared minus 30x plus 25 equals, determined to squeeze this in, what do I get? 4x squared minus 20. Right? Yeah, 4 times x squared minus 5. So that's 4x squared minus 20. 4x squared minus 20. And thus, what do I get? 5x squared minus 30x plus 45 equals 0. Divide through by 5, that gives me x squared minus 6x plus 9. And that's just x minus 3 squared equals 0. So, after all that work, guess what I just found? I just found that this function never crosses its horizontal asymptote, because the only time this function ever equals 1/2 or negative 1/2 is at x equals 3, but x equals 3 is just not even part of the domain of this function, so that's just a garbage extraneous solution. having done all that work, I'm now ready to do this graph. What does it look like? Well, it starts at time negative infinity, down at negative 1/2. So, boom, boom. Here we go. Down here at negative 1/2. This is negative 1/2. I'm negative until negative 3. I have a root at negative 3. I'm positive between negative 3 and negative root 5. And so this function just doing that. Boom. Whoa. Okay, now what? Now my function's just undefined between negative root 5 and root 5. At which point I pick up at x equals root 5 up here at 5/4. And then my function is positive. It stays positive forever after. It never crosses the horizontal asymptote y equals 1/2. Its end behavior is 1/2. And yet it's undefined at 3. But the local behavior of this point 3 is 3/4. So I get this kind of phantom point 3, 3/4, and that is a removable discontinuity, and that is the entire graph of this function, believe it or not. Whoa! All right, back in a second for the last page. Okay, here we go. Limit as x approaches negative 3 of 1 over x plus 3 to the 4th equals infinity. We need to prove this. Yeah, we kind of already did one like this, but maybe this one is harder or better, or I don't know what. So let's go. Let's go. First, we need to make a picture of this. All right, so you just need to know a lot of things, like that x to the 4th is going to look, kind of like this, a little bit like a parabola, but, steeper. And so, therefore, that 1 over x to the 4th is going to be the reciprocal of that. And so 1 over 0 is going to be like infinity, and we're going to get this kind of volcano situation. So what is 1 over x to the 4th? It's like a volcano, but a very steep volcano. All right, so when it comes to graphing my function, 1 over x plus 3 to the 4th, well, then the whole thing is just going to move over negative 3. So I get negative 1, negative 2, negative 3, and yeah, this function is clearly always positive. And what's it doing near negative 3? It's just becoming huge, because it's just like, duh. Plug in a number very, very close to negative 3. The difference between negative 3 and 3 is a tiny positive number or a tiny negative number, but when you raise it to the 4th power, it becomes an even tinier positive number, and 1 over that is going to be infinite. So the function, and you can even like plug in some numbers, like, I don't know, plug in like negative 2, then you get 1, right? And also when you plug in negative 4, you get 1. So all right, so some basic, that was a little bit extreme, but the idea is, yeah, it does kind of approach very, very steeply near, and then also, and then like, whatever. Okay, so what? What does it even mean to prove that this goes to infinity? Well, once again, you can play the game, right? If the limit as x approaches negative 3 is infinity, what does that really mean? It means that near negative 3, this function gets really, really big. How big? As big as you want. And so I'm going to get challenged with some massively large number m. And to meet that challenge, I have to get close enough to negative 3 so that this is true. So that's negative 3 plus delta, and that's negative 3 minus delta. Delta is how close to negative 3 I need to get in order to ensure that my function is bigger than m. All right, and therefore, what I need to prove is that for any massively large positive number m, that I have a delta response, that there exists some positive delta such that What makes this delta special? Well, it's how close I need to get to -3. So if x is any number in between -3 minus delta and -3 plus delta, but of course x not -3 itself, since the function's undefined there, but any other number in that interval, then when I plug it into the function, the output of the function will be bigger than the massively large challenge. Okay, good. So let's go. Let's go. How do we do it? Well, I'm going to have to do it with some kind of discovery phase, because the bigger my massively large number, then the closer delta has to be. And you can pretty much probably like guess pretty fast what the relationship is. Well, let's just do it. So what do I need to be true? I need it to be true that my function is bigger than m, where m is positive. Well, what's my function? My function is 1 over x plus 3 to the fourth. So when is 1 over x plus 3 to the fourth bigger than m? Well, just reciprocate both sides, and that's therefore true when x plus 3 to the fourth is less than 1 over m. Yeah. By just reciprocating both sides. Yep. And now what? Well, now I need to raise both sides to the 1/4 power. So yeah, basically just take the fourth root of both sides, and I get that x plus 3 that'll be true when x plus 3 is less than 1 over the fourth root of m. Now, because if I'm doing this proof sort of properly, then I have to kind of care about the fact that x might be a little bit more than -3, but x might be a little bit less than -3 also. And so if x plus 3 to the fourth is less than 1 over m, then what's really true about it is that it's like between -1 over the fourth root of m and 1 over the fourth root of m. Because, I won't say anything about that. I think that's just clear. And now, if I subtract -3, then I have the answer to sort of all my questions, right? The thing I was looking for is how close to -3 do I need to get in order to make this true, and this is the answer. Okay, and therefore I conclude from my discovery phase that I should set my delta to be 1 over the fourth root of m. And actually that just makes total sense, right? If you give me a massively large challenge number like 10,000, then the answer is the fourth root of 10,000 is 10, and therefore my delta response would be 1/10. So 1/10 is, maybe it's just worth it to just kind of write that out, right? If you challenge me with 10,000, then my response is going to be delta equals 1/10. 1/10 is intuitively how close to -3 I must get, because anything that's only 1/10 away from -3, when it gets raised to the fourth power, if the gap between my number and 3 is less than 1/10, well then 1/10 to the fourth is like 1 over 10,000. And the reciprocal of that will be bigger than 10,000. And if you challenge me with an even bigger number, like I guess I have to go now to like 10 to the 8th or something. So that's like whatever that is, like 10 million, no, 100 million. So, oh man, if you challenge me with 100 million, m equals 100 million, which is 10 to the 8th, then my delta response is going to be 1 over 100, etc. Okay, so of course the bigger the challenge, the smaller the delta needs to be, and discovery phase told me that is the key relationship to how I respond. Okay, so the value here is in sort of thinking through all these things and kind of understanding what we really mean when we say that the limit is infinite. Now it's just a matter of doing it. So I guess this problem's like pretty hard. There's a lot of technical details here. When it comes to doing the actual proof, what's going to happen? I'm going to accept a challenge. So take some positive m greater than 0, and immediately I'm going to turn around and I'm going to set my delta to be 1 over the fourth root of m. And now what I need to do is I need to show that it works. So I need to show that for any number between negative 3 minus delta and negative 3 plus delta, then my function is bigger than m. Okay, so this should mostly involve just doing the steps from discovery phase backwards, but let's really kind of approach it with a fresh mind. So assume that this is true. Assume that x is a number in between negative 3 minus delta and negative 3 plus delta, where x is not actually negative 3. I'm trying to do this problem by avoiding absolute values. Well, what is delta? It's minus 1 over the fourth root of m, and so that's 1 over the fourth root of m. Okay, and so now, I mean, I don't really know exactly what to do here, because, yeah, this is like a little bit awkward, because it is now sort of obvious kind of what I want to do next. What do I want to do next? I guess I want to reverse the steps from discovery phase and add 3 to all 3 sides. So what we get is this, right? Is less than x plus 3, which is less than 1 over the fourth root of m. And now what you want to do is you just want to use, kind of without justification, some kind of general principle, such as, suppose you were in algebra 1 or something, and someone told you that x was between negative 3 and 3. Well, it seems then that you should be able to conclude that x squared is therefore bigger than 9. But how exactly to go from here to here? Well, you could just do it and your justification is just duh, and actually that would just be totally fine. But if you really want to care about these kind of things, this is why mathematicians in math textbooks are always going on and on about absolute value, because the simplest thing to do now is to say that if x is between negative 3 and 3, then the size of x is bigger than 3. And if the size of x is bigger than 3, then x squared is bigger than 9. So if you like that kind of reasoning, then great. You could also, split this up into cases, I suppose, and say that, look, what I know now are sort of 2 things. That x is a positive number between 0 and 3, so that when I square it, it's bigger than 9, or it's a negative number that's between negative 3 and 0, and then for some reason also when you square it, it's bigger than 9. But okay, this seems like too much detail to go into here, so here I'm just going to go for it, and I'm just going to say, yeah, if this is true, if this number is between these two, then it's just true that x plus 3 to the fourth is less than 1 over m. It's the exact same logic as going on down below. If I can say that's so what everyone does in this situation, I'll just tell you, is they just invoke absolute values, because it just seems easier. That if this is between this and this, then the size of this is less than 1 over the fourth root of m. And that just kind of makes it all clearer. I've been trying to avoid using absolute values as much as possible because I feel like they're annoying, but maybe this is a great reason to have them. Anyway, to avoid cases and stuff. Now, if I raise both sides to the fourth power, then that tells me that x plus 3 to the fourth power is less than 1 over m. And if I reciprocate both sides, then my function, which is 1 over x plus 3 to the fourth, is bigger than m, and that is exactly what I wanted to show. So that completes the proof. Okay, oh my god, this review packet is going on forever. Is it absolutely essential to do calculus to be able to do proofs like this? Not really. But okay, let's erase this and let's just do the last problem from this packet, which is kind of also a technical sort of thing. Well, okay, yeah. The problem says, use the intermediate value theorem to prove that y equals x squared and y equals cosine x intersect. So whatever problem this was, the last problem, 17. Use the intermediate value theorem to prove that y equals x squared and y equals cosine x intersect. Okay, what is this even talking about? Well, let's make a picture. What does cosine look like? Here it is. Yeah, that's like pi over 2, pi, etc., -1, boom. So we're talking about something that looks like that. That is cosine. And then you have y equals x squared. And what does y equals x squared look like? Well, okay, pi over 2 is like about 3/2, so somewhere around here is like 1. And so I got something that looks like, already by here I'm at 1. By 3/2 I'm like up at 9/4. So my curve, y equals, this is y equals cosine x, this is y equals x squared. What you're tempted to do is just be like, dude, come on, duh, of course, they intersect. What is there even to talk about here? I just drew a picture. Alright, but how do you know that your picture, kind of like doesn't deceive you or something like that? Any reasonable person would end the conversation here and just say like, look, they intersect, of course. But how you know that they intersect really is because like there's no kind of like little points missing or any sort of like little sneaky jumps going on. In other words, what we're going to do is we're going to just invoke the properties of continuity. So maybe what we should do is like, give these like some names or something. So here we have the function fx equals x squared. That's continuous everywhere, in fact. And g of x equals cosine x. That's also continuous everywhere. So we have two continuous functions, and somehow the fact that they're continuous is like relevant for showing that they must intersect. And the idea here is that cosine starts below y equals x squared, but then later on, say at pi over 2, y equals x squared is bigger than cosine. And so really, this there's nothing special about y equals x squared and cosine. I just used those two functions for no particular reason. What we're really going to illustrate is a sort of fundamental idea that if you have one function, let's call it like, f1 or something, and it starts low and ends high, and you have some other function, f2, that starts high and ends low, then if these two functions are continuous, then they must intersect somewhere. And the reason is the intermediate value theorem, or at least one can show this with the intermediate value theorem. And the way you do it is with this kind of trick. And the trick is to show that the function representing the difference of these two functions has to be 0 somewhere. So we create a new function, h, and we say let h of x be, I guess it doesn't matter, on my paper I said x squared minus cosine x. Note that h is continuous on, and now I sort of pick some sort of interval. I'm going to use the interval 0, pi over 2. Why is h continuous on this interval? Because it's just the sum of two continuous functions, so it's also continuous. Okay, and now, what can I say about h? Well, what's h of 0? H of 0 is 0 minus cosine of 0. Cosine 0 is 1, so h of 0 is -1. But h of pi over 2 is... actually, I guess I could use pi. It doesn't really matter. But if I use pi over 2, then it's going to be, pi squared over 4. minus cosine pi over 2 is 0. And so here I have this picture emerging of this h function. What does the h function look like? At 0 it's negative 1, but at pi over 2 it's up here. And so now I say about this function that it must cross the line y equals 0. Cha. And so what we say is something like this. Since 0 is an intermediate value, it's a value between h at h of 0, which is negative 1, and h of pi over 2, which is pi over 2 over 4. So what I'm doing here is I'm telling you that there's this certain interval that I'm choosing to care about. This interval is the interval from 0 to pi over 2. That is pi squared over 4. That's the y value at the end of the interval. This is the h function I'm drawing a picture of. And this is negative 1. That's the y value at the beginning of the interval. And so if at time 0 my function is negative 1, and at time pi over 2 my function is pi squared over 4, then 0 is a intermediate y value. It's a y value in between those two. And so now we say by the intermediate value theorem, since this function is continuous, this h function is continuous on this interval, and since I picked a y value 0 that lies between the value at the left endpoint and the value at the right endpoint, the intermediate value theorem says that there exists a point C on the interval 0 pi over 2 such that f of C is 0. And so this is kind of like my value of C right here, cha. Okay, why is that helpful? Because, sorry, this should be h, I'm talking about, h function. So what do I know? I know that h of c is 0, but what is h of c? H of c is just c squared minus cosine of c. And if that's 0, then c squared does equal cosine c. And so that's what I needed to show. So basically, this problem is, there are two answers to this problem. Duh, of course they intersect, and okay, technically the reason why I know they intersect is because they're both continuous, and so they're not jumping around. And basically, two functions which sort of switch positions relative to each other, which is bigger, which is smaller, on some interval, must cross somewhere, is the general principle, and that general principle can be justified by applying the intermediate value theorem to a function which is the difference of those two functions. Goodbye.